So, good evening, and welcome to the May edition of the Slack Public Lectures. I'm very glad to welcome you here. Tonight, our speaker is Professor Bruce McIntosh from Stanford University and KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology, that owns this building that we have our auditorium in. By the way, for those of you who find this auditorium small or inconvenient, that big building that's going up over there is going to house our new auditorium, which will be roughly double the size of this one. And hopefully it'll be much easier to get tickets for a live presentation of these public lectures. So that's coming, we hope, in the fall, maybe for the November public lecture, so we'll let you know about that. So tonight's speaker, as I said, is Bruce McIntosh. Bruce got his PhD from UCLA, and then he went to work at Lawrence Livermore Laboratory in the very interesting program there on guide stars, on trying to put calibrated objects in the sky so that you could correct for atmospheric turbulence and have excellent seeing from telescopes on Earth. And he spent a lot of time developing this technique of adaptive optics. Now he's at Stanford and looking for planets using methods that have evolved from this program. So tonight he'll tell us about the search for exoplanets and the search for the atmospheres of exoplanets that we might be able to see. So Bruce, thank you very much.
Thank you very much for the introduction and the opportunity to talk here. Said I've only been at Stanford for about a year after being at Lawrence Livermore, another Department of Energy lab, for 20 years, and so I'm faintly nostalgic for visiting Department of Energy labs and seeing fences and guards and things like that, although, frankly, Livermore's guards much tougher than these guys, for good reasons. And so, yeah, I'm here to talk about the scientific research I do, astronomical studies of extrasolar planets using technologies like adaptive optics and modern state-of-the-art ground-based telescopes. And this is just a cover picture of the SOAR telescope in Chile, which is near the telescope I use, and in the foreground, Chilean condor, sort of 7-foot wingspan, adolescent bird that was circling overhead during one of our trips down there. And the best part of being an astronomer, frankly, is the opportunity to go down to these telescopes, because they're almost always in amazingly beautiful parts of the world, and then work very hard with very little sleep for a week or two trying to get the information you need before you go home. So I want to start with some history as I talk about planets, and I'll go a long way back for history, a couple of thousand years or so, to sort of the original view of the universe. And bear with me, we'll see why this is relevant to the way our modern view of the universe has evolved. And the original view was basically that there was the Earth, and that there was the rest of the universe, which went around the Earth, as you can see in these stylized diagrams. And that's not a terrible model. If you watch the sky for a day, it's pretty easy to see. Everything starts off in the east, rises up, goes overhead, and sets somewhere in the west, just like it would if you were circling around us. If you watch things on a longer time scale, you notice things are moving with respect to each other. There are fixed objects, stars, whose position relative to each other stays the same all the time, and they're moving objects, planets, wanderers, who over the course of a night move up like everybody else, but over the course of a year or part of a year, relative to the other stars, show tiny little additional motions. And those planets, figuring out where they were with respect to the Earth, was sort of the first great puzzle in astronomy. And in Ptolemy's model, they, just like the stars, went around the Earth. The problem is that that wasn't a very good model of their motions. If you watch Mars, for example, over the course of several years, it moves with respect to the stars, kind of like this, but then every so often it kind of goes backwards, and then it keeps on going with respect to the stars. And to produce a model that explained that, with the Earth here in the center, there's the Sun, there's the symbol for Venus, there's the symbol for Mars. If I start these planets running, you had to have them not just going around the Earth, but every so often deciding that they want to go backwards, that they make giant loops as they continue to go around the Earth and go forward, loops that were called epicycles by the person who produced these early models. Planets like Venus or Mercury have to do those epicycles quite a lot, Mars not so much. And so this sort of simple picture initially that everything was just going in circular orbits around the Earth failed very rapidly compared to observations. And of course, what really happens is everything doesn't go around the Earth, everything goes around the Sun. The Earth is here. As the Earth catches up with a planet like Mars, Mars will appear to move backwards with respect to the Earth. There's the Earth and Mars. As it goes further around, Mars will appear to go forwards, other planets going in their slow, stately orbits around the outer part of our system. And that change in the view, that idea that the Earth was not, in fact, the center of the universe, was one of the great revolutions in our understanding of just how humanity, how the Earth fits into the universe as a whole. And of course, that came about with people like Kepler and Copernicus. Copernicus, who initially had the idea that the Earth was kind of in the that the Earth wasn't in the center, we go around the sun, produced models that actually did an okay but not great job of saying, well, this is when Mars will start moving backwards, this is when it will start moving forwards. Kepler, who had a much more refined and mathematical approach, who actually did successfully predict things like he could write down the position of Mars every month over the next year with great accuracy and use that as proof that the Earth was not, in fact, the center of the universe. To scientists, that was a very compelling proof. It made a successful numerical prediction. He could make graphs. He could show positions on those graphs and compare them to theories. To the sort of broader public, that was somewhat less compelling. More compelling was, come on, computer, there we go, stuff that came from this guy, Galileo, the first person to take a telescope. And pretty much the first, and look at the stars. Pretty much the first thing he did with his telescope looking at the stars was look at Jupiter. This is a page from his actual observations night by night of Jupiter. And what he saw was Jupiter surrounded by 4 little dots. And the next night those dots had moved. The next night after that those dots had moved. The next night after that those dots had moved. Over the course of a series of nights, he realized what he saw was a whole system of moons orbiting around Jupiter. And just with his telescope, he could tell the Earth was not the center of everything, that other objects rotated around things other than the Earth. And it's interesting that demonstration, that actually seeing this movement with your eyes, was the thing that was compelling enough for the church to decide that he should be locked up as a heretic and treated as a danger to everything. So Kepler writing down equations, not so dangerous. Galileo drawing pictures and actually seeing the motion of planets, more dangerous and more compelling. And of course, scientists should never compare themselves to Galileo, but part of what we're trying to do is actually make that compelling visual diagram of what we see. Go forward. There we go. So at the time they were doing this, we had a solar system consisting of 7 objects, if you count the sun. In the center, the sun. In Copernicus's model, Mercury, Venus, Earth, Mars, Jupiter, and Saturn. By now we have, for a while we had 9 planets. We've settled down to 8, plus a bunch of these things called dwarf planets, which is a useful distinction because we see in our solar system, for example, that there are 4 planets close to the sun that are small. They're dense, they're made out of rock. We're standing on one. It's got a surface you can walk around on. It's got a thin atmosphere. And we see 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. They're large. They don't have a surface you can walk on. They're made out of hydrogen gas, methane, other elements like that. And then the handful of dwarf planets kind of complicating the picture, which is okay because they're not planets anymore. We also see, and Kepler noticed this, that these planets take different amounts of time to go around the sun. Fairly understandably, a planet that's close to the sun will go around very rapidly, like Mercury goes around the sun in a quarter of a year. A planet that's far away, like Neptune, will go around in almost 200 years. And when I was in graduate school, quite a while ago, I was taught, to the extent that I was taught anything about other solar systems, we didn't know of any at the time, of course, that they would all look like this, that this process that formed planets was universal, probably fairly common, and that all it could do is make solar systems that look just like our own with rocky planets and giant planets. We think that that process happens when a star forms. It's surrounded by a disk of leftover gas and dust that didn't quite make it into that star, and that gas and dust will condense, turn into lumps of rock or ice that will ultimately turn into a system of planets. There we go. In a sort of cartoon, you start with a big cloud of gas and dust. As it condenses to make a star, it flattens out because of physics. In the center, you get a nice hot thing that's heating up and becoming a star. That heats up the inner parts of the disk, but not the outer parts. And in turn, that means that common materials like hydrogen, oxygen, and carbon can be solid if they're in the outer parts. Solid hydrogen and oxygen is what we call ice. That's pretty common in the universe. Close to the sun, you can only be solid if you're made out of something like silicon or iron, which it turns out is much more rare in the universe. And so in the early solar system, there was a lot of solid stuff in the outer parts, not so much in the inner parts. In turn, that made it easier to make really big planets out of this common stuff, hydrogen, oxygen, carbon, in the outer parts, so you could make the big Jupiters out there and not so much anywhere else. And so as I said, I was taught that this process was pretty much universal. And astronomers, to some extent, weren't even worried about testing it 25 years ago. Only a handful of people were trying to study whether there were other solar systems. And that's kind of embarrassing, because it's a question that had been bothering people for sort of thousands of years. Do there exist many worlds, or is there but a single world? I would say is one of the most important questions in modern astronomy, even now. And there are a bunch of versions of this question that we can't answer right now, but ranging from, are there planets just like the Earth out there? Are there other planets that have life on them? That's probably the most exciting question I can imagine an astronomer answering, and it's a question that's probably going to take us 20 years to answer. But the earlier question of, are there solar systems like our own, we can answer, and the answer is yes. The answer is yes and no. There are solar systems, but they're not really a lot like our own. And I'll talk about the process through which we've learned that, the limitations of those processes, and what people like me do to try and answer that question in more detail. So the first way we find planets around other stars is wobbling. If you have a planet orbiting a star, like in this little cartoon animation, mostly the planet goes around the star, because the star's gravity pulls the planet, but the planet has gravity too, and so the planet's gravity pulls back on the star, as a result of which really they're not one going around the other, they're both orbiting around something called the center of mass, a point in between them where their gravity balances out. Of course, because the star is much, much bigger, the planet's gravity can't move it very far. The planet gets moved a long way, but the star is moving. And even if you couldn't see the planet, which in almost every case, except for some of the stuff we'll see towards the end, is true, you could tell the planet is there by this wobble, that something invisible is pulling it around and making it wobble. That's done by measuring something called the Doppler shift. So the Doppler shift you may be familiar with sound. The classic example is if a siren or a train with a whistle goes by you, you hear the pitch of that whistle change due to the motion of the train, motion of the ambulance's siren. The exact same thing happens with light. The light from something that's moving towards you gets just a little bit bluer. The light from something moving away from you gets just a little bit redder. That tiny shift, that Doppler shift in the light, can be measured by astronomers with modern spectrographs, for example, even at Lick Observatory above San Jose, the Keck Telescope in Hawaii, for motions as small as a meter per second. You can measure the motion of me walking around with one of these spectrographs. And the motion that Jupiter induces as it pulls on the sun and makes it wobble is much bigger than a meter per second, so people could see these motions from giant planets. This was done initially for a handful of planets almost 20 years ago now. They produced sort of beautiful, wow, we found extrasolar planets. There were these cartoons of huge planets. This one's got a moon that's getting evaporated by its sun. But of course, we didn't actually know that. All we knew really is that there was a planet there and roughly how big it was. Because when you make these measurements, I was told I was allowed about 2 or 3 graphs, so this is going to be one of them. This is a plot of the velocity, the speed of a star versus time. And what you can see for the speed of that star is that it's wobbling. Sometimes its speed is fast towards you, sometimes its speed is fast away from you, then fast towards you. And that's entirely due to the presence of this tiny wobble signal from the planet. And what they found from that first was that the period over which that wobble happened, which is basically how long it takes the planet to go all the way around the star, was incredibly short. Not like Jupiter, taking 12 years to go around the star, not even like a year the way the Earth does, not even 25 days like Mercury. The planet went all the way around the star in less than a week. And that was fairly astonishing. The second thing you learn from these graphs is how big the planet is. The bigger the planet is, the larger the wobble it will induce in its parent star. And this wobble was kind of medium big, 50 meters per second, not the 1 meter per second I quoted. And in turn, what that told us is these first solar systems had planets as big as Jupiter or bigger right next to their star, kind of practically skimming the surface of it. And over the course of several years, a bunch more of them were found. And that was a fairly astonishing surprise for the exoplanet theorists. In fact, these systems looked nothing like our own. They didn't have this clear two-class system between the gassy planets and the rocky planets. They had huge Jupiter-like things in a place where we thought they couldn't exist. And theory for planet formation has really been trying ever since then to explain these systems, and it hasn't really fully done it. So when you make that measurement, all it tells you is how much a planet weighs. And it only works if the planet's got this strong gravitational signal. A planet like the Earth, the wobble the Earth induces in the sun is too small to see with this technique, even with the state-of-the-art spectrographs. The signal from the Earth is on the orders of centimeter per second, and we can't measure that around other stars. The second way people found extrasolar planets was with something called transits. So a transit is taking advantage of an astonishing coincidence. As a planet goes around a star, could go around this way, but if through an astonishing coincidence it goes around like this, so it lines up between you and the star, then every time it goes around, for a tiny fraction of a second, it will block the light coming off of that star. And here's an animation. The star will get just a little bit dimmer for a few hours as it passes in front of it. Of course, the odds of that happening are nearly zero. The planet could be anywhere compared to the star. It would really have to line up exactly right. But if you look at a lot of stars, like 1,000 or so, and planets are common enough, then it will actually happen. And it turns out that this is a measurement that's really easy to make. For a giant planet like Jupiter, the star gets 1% dimmer. Stars are pretty bright. The nearby stars, you might choose to look at it. You can make this measurement with a telescope that's about this big. And in fact, people literally have. There was a chap who discovered one of these transiting planets from Pleasanton with his amateur-grade telescope in his backyard. More commonly, he only knew which star to look at because another astronomer had predicted there might be a transit based on some geometric arguments. But in general, these can be done with sort of 11-centimeter telescopes next to the giant telescopes on Mauna Kea. But the most successful example by far of doing this is with the NASA Kepler mission. Kepler looks at 100,000 stars. It does that by being in space with a huge camera, a gigapixel camera, the first one ever really flown by astronomers, looking at stars over an area much bigger than the size of the full moon, measuring their brightness with enough precision that it could see planets the size of the Earth, making the star get dimmer by a part in 10,000 or less. And over the course of its 3-year primary mission, it was spectacularly successful. It discovered a huge number of candidate planets, including potentially some that get down to the Earth-like scale. It does still have a limitation. No one will believe these detections unless you actually see that little dimming happen not once, because once could be a bird flying, well, not a bird because Kepler's in space, but could be some random glitch in the measurement of the star brightness. Not even really twice. You need to see the planet get dimmer 3 times in a row before you believe it's a real signal. The Kepler mission lasted for, in its primary phase, 3.5 years. Earth takes 1 year to go around the sun, so it could just barely see a signal from a planet out where the Earth was, and in fact never really reached the sensitivity for a true Earth analog. But close to the star, where planets would go around and around multiple times, it could build up the sensitivity to see something as small as the Earth. And although in our solar system to be habitable you have to be out where Earth is, close to a fainter star you could be a habitable, nice, comfortable planet closer to that star. And so Kepler produced a series of spectacular results, including press releases saying that in this shaded region sort of shows where liquid water could occur in a target system for a very generous definition of habitable conditions, and the size of a planet they found compared to the Earth. As one example, they found a planet, they just get serial numbers, Kepler 186f, that was basically the size of the Earth, basically in this habitable zone. Press release says Goldilocks Earth twin planet found, call the New York Times. Everybody's relatively happy about it. The problem, again, is that you don't get to know what these planets are made out of. All you really know is that there's something the size of the Earth blocking out the light. It could, in fact, be a rocky planet like Earth, but it could be a tiny version of Neptune made out of hydrogen or something like that. It could be made out of ice. It could be made out of cheese. It could have an atmosphere like the Earth. It could have an atmosphere of methane. It could have an atmosphere of carbon dioxide. It could be Venus. Venus is a perfectly nice planet, but you would not actually want to live on it, given the choice. And so with Kepler, again, we can't tell what these planets are made out of. There's a couple of very specialized circumstances where planets are bright enough to do that, but for almost every case, and especially the tantalizingly Earth-like ones, we can't do it. So what we want to do is take a picture of the planet. We want to actually see the light from the planet itself, because fundamentally that's the way astronomers study something. If you can see light from an object, you can tell what it's made out of, you can tell its temperature, you can tell something about its properties and infer something about its history. I'm not going to be able to show you examples where we do that for a planet like the Earth. This technique that we're using right now barely can get down to planets like Jupiter, but in the cases of planets like Jupiter, we can actually start to tell what they're made out of. And if we can see a planet in another solar system and see that it's a lot like Jupiter, we know the process that formed Jupiter in our solar system also made Earth, we can infer that maybe planets like Earth are common. And ultimately, 10 or 20 years from now, we could reach the point where we could use these same techniques to say an Earth. The problem is it's incredibly hard. Jupiter from outside our solar system is 1 billion times fainter than the sun, and it's right next to the sun, which is incredibly bright. And so the analogy that I'm required by the rules of astronomy to use is it's like you've got a lighthouse, and right next to the lighthouse, you want to see a firefly. And that's not a bad analogy. The light from the lighthouse from the star swamps the planet almost completely. So we need a way to actually overcome that and do that. There's several ways we do that, and I'll talk about the technologies. In the first phase of this, the first discoveries from this imaging of extrasolar planets, we mostly did them with the Keck telescopes on Mauna Kea and Hawaii. There's 2 of them, but usually only use one at a time, mostly that one in our case. A beautiful telescope. It's made its mirror that focuses and gathers the light from the star is made up of 36 hexagonal segments, each flat to a tiny fraction of the size of a human hair, coordinated by computerized controls, really the best optical telescopes in the world. The problem with these, even though they are the best optical telescopes in the world and Mauna Kea is the best place to put them, there's still a lot of air between them and the stars we want to look at, and that air blurs the image of something you look at. If I look at a star way off at infinity, with blobs of air between me and it, the blobs of air will bend the rays of light from the star and make a messed up image of the star, which would hide the signal from a planet almost completely. And that's where the adaptive optics technology comes in. Adaptive optics uses mirrors that can change their shape, not quite as severely as this mirror. This is an actual example you can see after my talk. It's a very thin sheet of glass, and glued behind it are an array of piezoelectric actuators, little pieces of ceramic that change their size when you put an electrical voltage across them. They grow and shrink, and in turn that makes the surface of this mirror bend by a tiny amount, a tiny fraction of a millimeter, but by enough to correct for atmospheric turbulence, like that. And so you can imagine taking all these distorted rays of light and bending your mirror just enough to bring them back into a sharp focus. In practice, it's a little more complicated than that. You take the light from the telescope, bounce it off this changing deformable mirror, but you need some way to know how to change the shape of the mirror. And so we use something called a wavefront sensor that senses the distortions in light, taking the light that has bounced off the mirror, seeing if there's any distortion left. If there is, a computer calculates the shape, sends it to the mirror to make it get back into sharp focus. The problem is that you have to do this 1,000 times a second because the turbulence, or 100 times a second. The air is always moving, so the distortions due to the atmosphere now are different than the ones 5 seconds ago, different than the ones they were 5 seconds ago. But computers, something we've been good at over the past 20 years, can do those calculations fast enough to make pretty sharp images. And then you take the rest of the light, send it down to a camera to make scientific images. And for example, here's the planet Neptune, a nice planet in our solar system, so easy to look at. Seen through normal Mauna Kea atmospheric turbulence, it's kind of round, not very round, but you can tell there's something there. It's got some blobs on its surface. If we turn on the adaptive optics system, it looks like that. So the resolution can improve by factors of 10 or more, making ground-based telescopes better in some ways, not every way, but better in some ways than the Hubble Space Telescope. That adaptive optics technology is part of what was pioneered by Lawrence Livermore and the group I used to work in. So if you look at a star with this adaptive optics on, it's a star. It looks like a little point. But that doesn't let you see a planet. To see a planet, you're going to have to massively overexpose the star and look for something faint like the planet. And if I do that with Keck data, I get images like this. So the little tiny star is surrounded by a giant halo of light, little scattered streaks and so on. And you can think of that basically as lens flare. If you take a picture facing into the sun with your camera, the lenses in your camera will blur and distort the light, dust on the lens, imperfections in the lens, reflections off surfaces, produce this big scatter of light around the sun. Same thing happens when you look at a star with a telescope like Keck. And this scatter, these blobs of light, are on the order of 10,000 to 100,000 times fainter than the sun. Than the star. That's a lot fainter, but I told you Jupiter was 1 billion times fainter, so we've got a long way to go before we could see Jupiter with this. The first trick we used is we don't actually look for a planet like Jupiter. Jupiter in our solar system is about 4.5 billion years old. It's cold because it's way out in the edge of our solar system, doesn't get a lot of heat, and so all it does is it reflects that tiny trickle of sunlight that hits its surface. When Jupiter formed in these disks of material that form planets, there's the disk, it formed very hot. The process of taking all the material, all the dust and gas that went into Jupiter, squishing it down to make Jupiter, released a lot of energy, a lot of gravitational potential and energy. So when Jupiter was newly born, it was probably at 3,000 degrees hot. After 10 million years, it cools off. It's radiating away that heat. It doesn't have a source of heat, but it's big, so it takes a long time to radiate away its heat. So a 10-million-year-old Jupiter is about 1,500 degrees. 100-million-year-old Jupiter is about 500 degrees. That's warm enough to give off a lot of light, especially infrared light, which is the kind of light warm objects emit. So at infrared wavelengths, a Jupiter that's 10 million years old is only about 1 million times fainter than the sun, not 1 billion. And that's a level of contrast we could potentially overcome. Not quite, though. If we just look at this lens flare image, here's a dot that could have been a planet but wasn't, way away from the star. If it had been a planet, it would really have to have been close in here, and you can see there's way too much starlight to overcome to actually see a signal from something as bright as a Jupiter-like even a young Jupiter-like planet. And so the next trick we use involves taking advantage of the rotation of the Earth. So I'm going to have to ask people to stand up, and I'm actually, if we get the lights dimmed a little bit, that would help for this trick as well, if that's feasible. So I'm going to talk about telescopes and the rotation of the Earth. So everyone who wants to can stand up. You don't have to, but it's good halfway through the talk to stand up. I alluded to the rotation of the Earth and what it does. The rotation of the Earth causes a star, here's a star, over the course of a night to rotate from the east all the way over to the west like that. Okay, so for purposes of this exercise, you're all going to be telescopes. And modern telescopes can move in two directions. They can rotate around their elevation axis, the up and down, and they can tip themselves up and down to try and track stars. So if I'm a modern telescope tracking a star, I rotate like this, and I tip myself up. Here's a star, and next to it, here's a planet, very far away, so it's easily detectable by all of you telescopes. You don't really need fancy image processing. So I'm going to start moving it across the sky, and I'd like you to rotate your bodies to track it. Before you do that, notice which side this planet is on. Planet's sitting there on the left side of the star. So let's all move like this, rotate our bodies, rotate our heads. You'll notice as it goes overhead, you have to spin pretty fast. And then as it starts setting again, you spin more slowly. You've now followed a planet and star system over the course of 12 hours. Now where's the planet? It's on the right side. So over the course of time, you can all sit down now, things that are real on the sky appear to rotate. With a normal telescope, if I wanted, say, to take a picture of a faint galaxy or something like it, that's actually a problem, and you would counteract that by taking the spectrograph or the camera to look at your faint galaxy, rotating it in the opposite direction so the image would stay the same on the camera all the time. We don't do that. We actually turn that off. And the reason we do is that the lens flare, the artifacts stay fixed with respect to the telescope, while the planet will move. So if you had had lens flare, if you had really bad eyes and you're looking at my laser pointer, you would have seen a skew of rays coming off of it. They would have stayed fixed because they're coming from your eyeball, so they're always in the same position on your retina. The planet would have moved. And so I'm going to show some data sets that show that for real. This is a couple of hours of data as the Keck telescope tracks a star. You can see the lens flare holding still. Everybody see that? Yeah. So that's real. Let's let the movie start again. And now look up here. So this guy you could have seen, but there's no chance you would have been able to detect that one out there without taking advantage of this fact that it's moving, it's pivoting as the Earth rotates. Not as the planet goes around the star. This is just a few hours as the Earth rotates. And so if I'm good at image processing, or if I hire a postdoc who's good at image processing, which is what I do, you can write optimal image processing filters that will look for all the stuff that's static in this image and remove it and leave behind the dynamic stuff. And that's what this image is here. So these are exactly the same images, but with a temporal filter applied to remove stuff that's static and leave behind the moving stuff with some complicated signal processing applied on top of it. Blip, blip. Once in the audience, I've had people see planet number 3, but I don't think that's very likely to happen, so we'll go forward. This is the same image set, but now rotated so that north is up, and so planets stay fixed and added together. And over the course of an hour or so, the remaining random components of the noise go away, and you can pull out signal number 3. And those are real. So every one of those dots is a planet. In fact, there's 4, although the 4th one takes a lot of image processing to see, so I can't show it in the demo. But this is a system of 4 extrasolar planets orbiting another star. The star is called HRID 799. It's a boring name because it's too faint to have a real name. The planets, even more boringly, are called HRID 799 B, C, D, and E. Currently, we don't let astronomers give names to planets, which is probably okay because I would have named them after my dog or something. So my daughter wasn't born at the time. But the fact that we can see them is pretty amazing. The star is here, and there's a little bit of light left over from the star. The adaptive optics isn't perfect. The image processing isn't perfect. So these blobs are leftover starlight. But this is the real infrared signal from a glowing planet. The star is a little bit bigger. It's about 50% more massive than our sun, a little bit hotter, a little bit bluer. The planets are also pretty big. They're sort of 5 or 7 times the mass of Jupiter, and they're warm, the 1,000-degree temperatures. The star is about 30 million years old. The outermost one you can see is a little bit fainter because it's a little bit less massive and a little bit cooler, but we can see them. We have data for these. Let's see, I can gratuitously compare it to our own solar system, which astronomers love to do. It kind of is like, it's like a scaled up version of our solar system. This version of the other system has been magnified proportionally. The planets are obviously much bigger, but it has other features. We know from various lines of other evidence that there's a belt of asteroids in this system, and it's located, it was known before we found the planets. What we found is it's located right inside where the innermost planet is. Exactly the same way asteroids in our solar system are right inside the orbit of Jupiter, because Jupiter keeps them there. We found, there was evidence again before we found the planets of a belt of comets way in the outer part of that solar system, and that belt of comets is kept out there by the outermost planet, the same way comets are kept in the Kuiper belt in our solar system by Neptune. So in some ways it is a scaled up version of our solar system. In other ways, not so much. It's only 30 million years old. There's about 100 times as many asteroids going on random orbits as there are in our solar system. There could be an Earth in here, but if there is, it's an Earth that's getting smacked by an asteroid as big as the one that killed the dinosaurs pretty much every 10 years or so, so it's not habitable yet. But the Earth wasn't habitable 30 million years ago, 30 million years into its history either. And in fact, we have data for this system going back to 2008. In that data, you can actually watch these planets orbit, and they're doing what Kepler said they would. The one close to the star moves fastest. The one farther from the star takes the longest time to go away. It's not a surprise that Kepler's laws actually work, that they work in other solar systems. But the fact that we can see it, not like the animation I showed you, everything goes around the sun from outside, but for real, everything going around another sun for real is probably the most amazing thing I've seen in my astronomer career. With that, so what can we learn about the system using these techniques? Well, we can study their orbits. One thing we find, again, unsurprising from Kepler's laws, is that we're not going to be able to see the whole orbit. The outermost planet, we've watched it for a tiny piece of its orbit because it's going to take 800 years to go all the way around the star. The innermost planet that we've found so far will take about 40 years to go around the star, so I'm trying to exercise and eat better so that I can actually watch it do an entire circle, which would be cool to see. Maybe I'd like to see it do 2, but let's not be too ambitious. I'll talk about my real strategy for seeing multiple orbits towards the end of this. And so because we've only watched them go partway around, there's a lot of uncertainty in how their orbits are going to go. But I can take, so these are all possible orbits, ways the planets could go into the future. I can take one of those, or my postdoc Quinn Konopaki can, and my former postdoc, now she's a professor at UC San Diego, and predict what their motions will be. This movie is going to take a while to get started. Oh, no, it started. So this is a simulation of moving one of those possible orbits around into the future, and the planets are tugging on each other because they have strong gravity. And in fact, they're tugging on each other enough that we just lost a planet, so what was a 4-planet system has now become a 3-planet system. You can see them continuing to tug on each other. Their orbits are changing in a way that orbits don't in our solar system, as a result of which we're now down to maybe a 2-planet system. This simulation only took about 3,000 years to show that, and of course that's not realistic. This system's been here for 30 million years, so the odds that it's going to fall apart in 2,000 years are essentially none. Still got 3 planets. Which says there has to be something wrong with this simulation. And what was wrong with this simulation is that we made the planets very big. When we published this, people said, are those really planets? Maybe you've just found tiny stars. And so we ran a simulation with tiny stars, and we found the gravity of tiny stars is strong enough that the system would fall apart almost immediately. Hence, we can infer that they have to be something like 5 times the size of Jupiter, that they can't be giant planets. Yeah, we don't really need to see that again, though I like it. So I promised, so we had a press release too, and so we had our cartoon, here's the planet, here's more planets, beautiful. You can see them glowing because what we're seeing is the hot infrared radiation coming from the inside. Of course, initially when we saw them, that's not what we know, we just know there's a planet there. But because we can see the light, we actually can figure out what's going on in the atmospheres of these planets. Anything you can see light from, you can study. Astronomers do that using a technique called spectroscopy. So spectroscopy, some of you know from your physics classes, if you have some cloud of hot material like gas from a star, and you disperse that light through a prism, spreading the wavelengths of the rainbow of light out from red to blue, different elements only emit light at certain specific wavelengths. And here's a stylized cartoon of that rainbow and a graph type thing of the intensity versus wavelength. So where the light is bright, the intensity is high. At other wavelengths, there's no light. And those spectra are fingerprints of particular chemical elements. Helium has its own fingerprint, sodium, the sodium traffic lights you see in San Jose have a fingerprint, neon has a fingerprint, and so on. And so by seeing what wavelengths of light are present in an object, you can tell what it's made out of. In the case of a star or planet, it's slightly different. What you actually see is the hot inside of the star or planet glowing through the cold top of the planet's atmospheres. And so rather than seeing bright lines, you see dark lines where the cold gas absorbs particular wavelengths of light. But it's the same thing. The same wavelengths of light get absorbed based on the chemical footprint. And doing this is what told astronomers what the sun was made out of. We never really sent a spacecraft to pick out a piece of the sun, but we know what it's made out of because we can see those footprints. We're never going to send a spacecraft to other stars. We know what they're made out of. You can see those fingerprints. And we can do the same thing for planets. Here's the image without the fancy image processing, but the outermost planet you can see. I can line up the field of view of my spectrograph, lock it onto the planet, and see what it's made out of. And I can actually take advantage of the way light works to enhance the signal from the planet even further. Here's the image I get through my spectrograph, but the kind of spectrograph actually makes not just images and not just spectra, but combined images and spectra. The technical word is hyperspectral cubes, where for every pixel in this image, I learn what the brightness of light is at all different wavelengths. And I can show that by animating. Go forward. There we go. When I do that, I find that the scattered light, the lens flare, actually has a very characteristic behavior where from short to long wavelengths, this is an animation going from short wavelength light to long wavelength light, lens flare light moves. It moves away from the star as a function of wavelengths for physics reasons. Planet, of course, is always at the same position for every wavelength, and so I can do exactly the same, or in reverse, I do the trick of show me the stuff that's holding still, get rid of the stuff that's moving, and pull out the planet signal in the spectrograph very beautifully. And in turn, I can unwrap it, this is my second graph that I'm allowed in these talks, into a plot of a spectrum, an intensity of light versus wavelength, versus infrared wavelengths of light. Some wavelengths of light we can't see the planet because we're down on the Earth, and the Earth's atmosphere is full of water vapor, and that absorbs infrared light at some wavelengths, so that's why there's a gap here. But you can see even before you get to the gap, the planet is getting dimmer. And what that's actually telling us is there's water in the atmosphere of the planet, absorbing the same way it does in the Earth's atmosphere. Of course, water, because this has a temperature of 1,000 degrees, really means superheated steam, and planet is something that's much bigger than Jupiter, so it's not like, call the New York Times, we found water. It's just evidence that hydrogen and oxygen, when you put them together, form water vapor. But still, we can see that chemical footprint in this super hot planet. We can see a chemical footprint of carbon monoxide. We don't really see a chemical footprint of methane, which we expected to see based on the planet's chemistry, and in turn that's telling us the way the planet's atmosphere is circulating is destroying methane molecules, the carbon monoxide. We did see, and a lot of the radiation we actually is evidence, we think, of clouds of liquid metal, basically. The atmosphere of this planet at 1,000 degrees or 2,000 degrees deeper inside is hot enough to melt iron or silicon or things like that. There are clouds of droplets of liquid metal sitting there producing the radiation that we actually see. So a couple of other planets have been seen with this technique. This is one called Fomalhaut, basically seen around the same time ours was using the Hubble Space Telescope by Paul Kalis at UC Berkeley. Fomalhaut also has a ring of comets and dust, and just inside that ring, the Hubble Space Telescope saw a tiny dot that moved over the course of 2 years, indicating that probably was a planet. Another one could have been discovered in 2003, although the image processing technology wasn't there, but there was a little blob. Here's a star, image processed, so most of the star is gone. Little blob was on one side of it in 2003, and they kind of wondered, what was that little blob? They weren't sure. In 2009, when they came back, the blob was on the other side, and we now know it's a planet that orbited behind the star, was lost in the lens flare, and is now going to orbit around the other way. This system also has one of those dust and comet belts, in this case almost exactly edge-on. We're seeing this solar system from the edge geometry lined up just right at us. That's another example of a giant planet. There's now half a dozen and more to come. So these planets are pretty cool, but again, they're not quite like our solar system. They're giant planets out where the outskirts of our solar system goes. The outermost guy in HRD 799 is where Pluto was when it was a planet, beyond where Pluto was. In fact, even the Beta Pic one is sort of between Jupiter and Saturn. What we'd like to see is what's going on in here, where Jupiter is in our solar system. And that's the next part of my talk. An instrument called the Gemini Planet Imager was built to do this. After we reached basically the limit of what we could see with Keck, we tried to build a new instrument, a new adaptive optics system. It's on the telescope called Gemini South. So telescopes, it's kind of like SLR cameras in reverse. You buy a telescope, which costs you $100 million or something like that. You build it at a place in Chile, and then you can attach different cameras or spectrographs to the back of it. So you might have a special camera designed to study very faint galaxies. When you get tired of studying very faint galaxies, you might build a special camera to study planets. And that's what Gemini did. The Gemini Planet Imager is a combined adaptive optics and camera thing intended only to look at planets, and hence to do a very good job of it. This is kind of what it's like. There's a person for scale, or a robot in this case. This is the back of the Gemini telescope, has a cube for mounting instruments. The whole thing's in an enclosure to keep dust out, because a tiny speck of dust would look an awful lot like a planet, so you keep the equivalent of a Class 100 clean room inside it. Cabinets for the computers, and inside it the instrument itself. The instrument contains an adaptive optics system. It was built by Lawrence Livermore National Lab. much more powerful, and I'll show you why, than the adaptive optics system we had at Keck. A set of special masks built by a team at the American Museum of Natural History that block the light from the star. A precision wavefront sensor JPL built to measure tiny little biases in the light. An infrared spectrograph that UCLA built. And finally, a group in Canada built the whole mechanical structure that holds the thing together and the software that holds the thing together, which is arguably more important than the mechanical structure. There's 20 person years of code sitting in the middle of this to make it actually operate. So I mentioned the adaptive optics being more powerful. So this mirror I'm holding up here has 18 of these little piezoelectric actuators, degrees of freedom to control the atmospheric turbulence. The mirror that we use at Keck has 300 of them, and it's about this big because each of those actuators is a centimeter apart, so you want 300, it's got to be this big. To really do good planet detection, to go beyond what we could do at Keck, we figured we needed 4,000 of those actuators, 4,000 degrees of freedom. And so if I built it with that technology, the mirror would be this big, and it wouldn't really fit in my instrument. I'd need huge lenses to get the light to and from a mirror that big, lots of distance to focus the light. Our mirror instead is this big. This is a 4,000 degree of freedom deformable mirror, but made with incredibly different technology. This is made out of silicon. It's a microelectromechanical system. It's basically a microchip mirror, lithographically manufactured, kind of like the mirrors TI puts in projectors like this one, but much more precise than the TI mirrors and many fewer degrees of freedom. And so physically something this big has 4,000 little individual actuators that can move up and down and shape and control the light in response to signals from our computers. And that lets us build the Gemini Planet Imager on a scale that's actually feasible. The masks to block starlight, they're also fairly complicated. They're little grayscale patterns of dots that basically smooth the light from the telescope so that the lens flare gets blocked. We focus the light from the telescope on a mirror with a hole in it, so the star falls down the hole. The planet gets focused off to the side and keeps going, so we can separate the planet from the star using that trick. We put the whole thing together at UC Santa Cruz in a clean room. Wasn't clean at this time, obviously, but this is just before we made it clean. And there it is sitting in its enclosure, computers, the front of the instrument, the things to keep it clean. The spectrograph was built by UCLA. Turns out when you want something painted, made out of metal in Los Angeles, you go to a company that does sports cars, and so it's painted midlife crisis red. Made the guy in charge happy. An infrared spectrograph is a very complicated beast. For example, because warm objects make infrared radiation, you have to cool the inside of the spectrograph so it's not warm. And so inside it operates at a temperature of minus 200 degrees in vacuum so that the detectors can keep operating. It's going to go on the back of a telescope. It has to keep working as the telescope points at different stars, so we put it on a crane, tilted it all over to make sure nothing fell off, make sure it stayed aligned. It has to operate in a wide variety of conditions, so we built in Santa Cruz a giant meat locker around it to chill it down to sub-zero temperatures and show that it would continue to operate, which it did. After that, we packed it up, put it in crates, got it custom crates to ship it down. My small child helped with the process of loading it onto the truck. There's the truck. It didn't drive all the way to Chile. You can't do that. So we drove it to Los Angeles, loaded it on a plane, flew it down, stopped briefly at Lima, Santiago, and then a truck up to La Serena. I did not travel with it because I don't speak Spanish. I don't understand Chilean customs, and watching 10 years of your life get pushed around by forklift drivers is not a very relaxing process. Got up to the top of the mountain safely, and there I did come down to see it and show that it survived its trip successfully. We put it on the back of the telescope. We have a Facebook page, by the way, as well as a web page if anybody wants to watch this. This is the Gemini telescope. Its mirror is here. The back of it actually has room to mount 5 different cameras or spectrographs, and they can switch between them, which is very nice, so we can put ours on and test it while they continue doing regular science observations successfully. First light, which is what you call it when you actually see stars, happened in November of 2013. For first light initially, here's our large team, really excellent people working on this. We concentrated initially on the planets we already knew we were there. So for example, the Beta Pictoris planet, that's the one that was orbiting in this disk of dust and comets that is right lined up with the star. Here's what we saw. Here, these are just 4 dots that are there to calibrate the instrument, so you should ignore them. We didn't discover 4 new planets. But here is the star falling down that hole, kind of glinting off the edge of the hole. And here, that signal, that's a planet, about 10 times the mass of Jupiter. For comparison, I said we knew about this one before, so here's an image from a previous Gemini instrument showing the same planet. Our image is clearly substantially more sensitive. But this is an hour of telescope time with all of the fancy image processing that I talked about. This is the raw data coming off the back of GPI in 60 seconds. So really, we're doing substantially better. If I actually take the whole half hour, process and stack, I get something like that. And so we were happy. We can now use this. We can study beta Pix B's spectra. We can study its atmosphere. For example, here's a plot of its, oh, I did 3 graphs. Damn it, I've cheated. All right. This is a plot of the position of the planet in x and y coordinates versus time, basically showing its orbit goes separation from the star. The star is here versus time. So it passes behind the star, comes around. We're observing it now in 2014. In 2017, it's going to pass in front of the star, and there's actually a decent chance that this one might line up in that exact right geometry so that it will block the star for, in its case, a few days, because it'll be moving fairly slowly. And if that happened, that would be amazing, because we could then constrain the models of planet formation very precisely. May not happen. Another thing we can see with GPI are these dust and comet rings. Here's an image of a star falling down the hole. This is not an artifact. This is a ring of dust produced by comets and asteroids orbiting around another young star with another serial number type name, HR 4796. We can look at it not just in ordinary light, but in polarized light. So from polarized sunglasses work because when light reflects off something tiny like light, like little particles in our atmosphere, it gets polarized. The light gets oriented in a specific direction that can be blocked by special pieces of glass, polarization filters. GPI basically has one of those that lets me see that work in the other direction. They only let polarized light through. And if I activate that, I can remove all of this leftover starlight and see just the dust ring. But interestingly, only on one side. The dust ring is very bright on both sides, but only polarizes on one side. And we're working on models to explain that. We think what we're seeing is a ring of dust tilted like this. As light comes from the star and sort of grazes a dust grain and comes towards us, that will polarize it very strongly, especially if the dust grains are big and fluffy things like you might have left over from a comet in that other solar system. If light hits a dust grain and comes towards us, it bounces, but it doesn't really get polarized in any particular direction. So we can use that polarization signature to understand these dust particles. GPI's been on the telescope for a year and a half. It's looked at a whole bunch of interesting systems. Again, here's a picture of the team, Chilean Wildlife. It's a large project. When you run a project for 10 years with 60 people on it, not all of them make it to the end to see it, which is kind of a sad thing, but there are a lot of people who contributed and deserve an enormous amount of credit. And simulations say that we should find between 10 and 50 planets, really, that are getting close to being like Jupiter. So in the last few minutes, if it's okay, I'm going to talk about the next couple of steps in the future. So I'm going to go back to space. So Kepler, as I mentioned, incredibly successful at counting planets. And one of the amazing things it found when it counted planets is that there's a huge number of planets whose size is in between Neptune in our solar system and Earth. If you're an optimist, you'd like to call those planets super-Earths and think that they're big rocky worlds you could live on. If you're a pessimist, you might call them micro-Neptunes. And the reality is we have no idea because we can't tell what they're made out of. And there's nothing like that in our solar system. The biggest surprise of Kepler is that the most common planet in our galaxy is something that there's no equivalent of in our solar system, and we'd like to know what those are actually made out of. For Kepler, that's hard, in part because all the systems Kepler finds are far away. I talked about how Kepler wants to look at thousands of stars to get this incredible coincidence of transits. It does that by having a pretty big telescope looking deep into our galaxy so that it can add up thousands and thousands of stars. Very sensitive. It can see stars much fainter than you can see with the naked eye and still make these precise measurements of their brightness. But because of that, the stars are necessarily quite far away. The next thing after Kepler in space is going to be something called TESS, the Transiting Exoplanet Survey Satellite. It will also look at 100,000 stars, but the way it will get 100,000 stars is by looking at the whole sky. If you go over the whole entire sky with your eye, you see about 2,000 stars, but only a little bit fainter than that, you can get down to 100,000 stars. Rather than even being a telescope, TESS is almost like an array of big 100-megapixel SLR cameras, basically, all pointing in slightly different directions, all taking a picture of the sky, move, take another picture, move, take another picture, and look for a star that's getting a little bit dimmer. Once it does that, the planets it finds will be close, and so we can look at them with other telescopes, like GPI, or like the James Webb Space Telescope when it flies in 2018, and so on. And so we might be able to tell what they're made out of. I think I'm going to skip this video in the interest of time, but there's a very cool video of TESS surveying the whole sky you can find on the internet. The next step beyond that potentially would be even bigger telescopes on the ground. The Gemini telescope is about 8 meters in diameter. That's close to the state of the art. But astronomers would like to build bigger telescopes. If you built one that was 30 meters in diameter, this is you can guess how big this telescope is from its name, the 30-meter telescope. It would, and put something like GPI on it, it could see not just the Jupiters, but at least the Neptunes and probably the super-Earths, if that's what those planets are. Construction for the 30-meter telescope, the lead US partners are Caltech and University of California, plus a bunch of international partners involved in it. Construction is currently paused. It's being built or proposed to be built on the mountain of Mauna Kea in Hawaii, which is a mountain that people in Hawaii have a considerable cultural importance attached to, and so we're trying to negotiate. Not we, I'm not involved in this, we're trying to negotiate how to deal with that considerable cultural importance. It's a complicated issue. There's other equivalent telescopes that will go on mountains in Chile that nobody is that significantly attached to, so there definitely will be telescopes in this class built by some institution somewhere. Not the US federal government. The US federal government is not participating in these projects. They're almost entirely private or international. Not Stanford yet either. And so those might reach into the point of TMT, seeing the sort of Neptunes, TESS, seeing the super-Earths, and learning what they're made out of. To go beyond that, the last two things I want to talk about will require telescopes in space again, but the combination of the light blocking that I do with a decent-sized telescope in space. The problem with that is 5 years ago, when astronomers decided what their priorities were for the next decade, planet detection was uncertain enough that it didn't become a priority. So the highest priority for astronomers in this decade and the next is something called the Wide Field Infrared Survey Telescope, whose name pretty much tells you what it does. It surveys the whole sky in infrared radiation. It's oriented towards studying dark energy, expansion of the universe, galaxies. Very important to lots of people in this building. And it's definitely yeah, we should do it. It's a good project. At the budget we had at the time, astronomers had at the time, NASA could afford to build about a 1 meter, 1.2 meter telescope to do that. And that's big enough to survey galaxies. It's not big enough to see planets through direct imaging. But something interesting happened 2 years ago. So by analogy, I could explain this. You might go to your closet and discover in your closet that you have a lot more shoes than you thought you had because you bought a bunch of shoes, you never wear them. And you might say, I don't need these shoes anymore, and so you'll donate them to a charitable organization or to a friend or something like that. Basically, the same thing happened to the Department of Defense, except instead of shoes, they discovered they had a warehouse full of Hubble Space Telescope-sized telescopes that they weren't actually using and had no plan to use in the next ever. And so they donated 2 of these to NASA. They didn't donate whole spacecraft. They're just the assembly for a space telescope. And so NASA still needs to wrap a telescope around them. But that lets them do this dark energy mission that they wanted to do with a telescope 1 meter this big, with a 2.4 meter telescope this big. And that's big enough that you could start to see extrasolar planets with it through the direct imaging techniques. In addition, it can do the dark energy stuff much faster because it's a bigger telescope, so there's more time available to do other kinds of astronomy. And so the plan is to fly this. It's something that will be called, again, I think I'm going to skip the video in the interest of time. There's cool NASA videos about it. Come on, skip, there we go. It's called the Astrophysically Focused Telescope Asset right now. It'll get a name when it actually flies, as is traditional. And it could get down to the point where it could do this spectra trick, but not with giant hot Jupiters, but with Neptunes or maybe super-Earths, and see what's actually present in their atmosphere, what they're made out of at high levels of fidelity. And so that would reach probably still not the Earths, but well into the super-Earth regime, around stars like the Sun, in the neighborhood of the Sun. Probably just a couple of them because it's not that big a telescope. The next step beyond that, if you're really going to see an Earth, you have to block the star out almost completely. So blocking stars out almost completely is something actually a lot of us do. Let's say you see a bird and it flies next to the sun, you want to see it. What do? You do this. You hold up your hand, block the star. So that's what astronomers want to do next, and I am going to run this video because it's very cool. The next mission beyond that might involve a space telescope and a whole separate spacecraft that is basically a giant hand, not shaped like a hand because that would be silly, intended to block the star. It's actually shaped very precisely to block the light, involving ways light diffracts and bends almost exactly. And for it to work, it has to be 50,000 kilometers away from the telescope to block just the star and not the planet on a reasonable scale. And so the engineering challenge of doing that is enormous. It has to be about 50 meters across, but enormous but solvable. And if you did that, you could block the star and actually see not just the Jupiters, but a planet potentially the size of the Earth. And so if I'm doing a version of this talk 20 years from now, the image I might get to show is something like this, where there's a star just leaking around sort of through the holes in that star shade. The enormously bright one that you couldn't possibly miss is Jupiter, a billion times fainter, reflecting its starlight. There's a Venus, and that one actually is an Earth poking its head around. And once you can see it, just like we can with the HRD 799 planets, we can put a spectrograph down, we can see what it's made out of, and we might see oxygen, we might see water, we might see chlorophyll, we might see life. So I think that's where I'll stop, and thank you all very much.
So Bruce, thank you very much. We have time for questions. So the deal with the questions is the following. There are people with microphones on both sides of the auditorium. Raise your hand and get recognized, get a microphone. Don't start your question until you have the microphone, because this is being recorded, so no one will hear your question unless you speak it into the microphone. So please, who'd like to ask a question? Let's start here.
Do most biologists believe that if you see oxygen, it's a sure sign of life, or are there other possible mechanisms that could create O2?
Right. That's a complicated question, and almost certainly it's far too simplistic to assume oxygen exists only due to life. If all life on Earth disappeared, Earth would lose its oxygen. It would get bound up into carbonaceous materials in the oceans on a fairly quick time scale, I think 10 or 100 million years. That's not to say there aren't other chemical processes that could produce it. Or methane is another one people think could be a biological signature, but there's other processes that could produce methane. So the reality is, now that I'm moving beyond the optimism, when we find these spectra, there's going to be huge amounts of argument about interpreting them. And it may be nowhere near definitive. Nonetheless, oxygen is so reactive that you need a source to maintain it. We think that source could only be life, but we can't know for sure. If you saw oxygen and methane, you'd probably think you have to have a source, but again, we can't know. I mean, methane maybe is a biosignature. We kind of see methane on Mars. We can't decide if there's life on Mars or not. We can drive there, right? You can put a truck on Mars, drive it around. We're not sure if there's life or not. So it will be challenging, and it probably will take not just simple spectra, but very high sensitivity spectra. But once you start to see all those chemical footprints, I think you could make a strong case. People have done simulations that show you could see the chlorophyll in the vegetation on the Earth does make a detectable signal in the Earth spectrum. You'd probably need enormous telescopes, 100-meter telescopes in space to actually be sensitive enough to see that, but it's not unimaginable. So it will be, even 20 years from now, a step, but I think an important step. If you could see water and oxygen and methane, you'd at least think it's possible that there's life there.
Please.
Are the radio astronomers doing anything useful for planets?
Radio astronomy. Actually, there are, now that, depending on your definitions of radio astronomy, but millimeter, sort of microwave radio astronomy can see emission from medium warm things like dust and gas. And so there's a brand new millimeter telescope in Chile called ALMA, the Atacama Large Millimeter Array. And it's one of its most exciting science processes is it could map out these cartoons I showed you of planet formation, showing those gaps opening up as the planets form. It's actually produced an image that shows that around a star 150 light years away. So radio astronomy will be very powerful for studying the formation of planets, which is part of the puzzle of planetary systems. Mature planets, and even medium young ones like the HRD 799, are beyond radio astronomy right now. Jupiter does emit radio waves, but the signal is so faint you couldn't really detect it from another solar system. So the power of radio astronomy mostly lies in the formation of planets in those first few million years.
Over here, would we ever be able to see moons around these gas giants the way Galileo saw the Jovian moons?
Directly separating the moon from the planet is probably extremely hard because of the relative ratios of brightness and separation. There's actually a debate about this in an exoplanet imaging Facebook group, so I can cite definitive Facebook sources. There are a couple of special cases where maybe we could. Io, one of the moons of Jupiter, is really hot because Jupiter's gravity squeezes it. You push it really hot, in this case means it has volcanoes erupting on its surface. You pushed it closer to Jupiter. Before it was destroyed, it would probably get incredibly hot, and you might actually be able to see that infrared emission as an excess in infrared light compared to an old planet like Jupiter. And then maybe we could get lucky. We could have the same geometry of transits, except with the moon passing in front of a planet, you'd see a planet get 1% dimmer every 12 or 24 or 36 hours. as a moon goes in front of it. And you could actually imagine the beta pic system seems to be lined up pointing at us, so if there were moons, they might do that. It's right on the edge of what we could measure with GPI. I suspect the signal would be slightly too small for GPI, and you'd really need the telescope for a whole month to do it, so they're not going to let us do that now. But with the 30-meter class telescopes, I think the consensus was we could see that kind of signal from a moon.
I have two questions. First, how close are we to sending someone out of Earth to like study the different planets and what kind of composition they have? And the second thing is, if we can one day send someone out into space, what would be the biggest challenge besides radiation protection?
And sending people to, or even robots, to other stars is pretty far beyond our current technology. If you're traveling at even a good fraction of the speed of light, it would take you hundreds of years to get to the HRID 799 system. And so we can't build spaceships that can travel that fast, and we can't build systems that would keep running that long. But challenges are relative. I think it's not unimaginable in a couple of hundred years we could be launching probes to other solar systems. Not with people. The probes would be computers. One of the things that, if you think about areas technology that are advancing, rockets, they're getting a little bit better. Computers are getting a lot better. And so the ability to send a small computer that's smart enough, as smart as a person, to study a solar system, I think is not at all crazy on 100 or 200 year timescales. And there's a bunch of technologies you could imagine using for that. Sending people, I think there's no technology that would make the trip take less than hundreds or thousands of years. And so figuring out how to keep people alive, or their children alive, or their children's children for hundreds of thousands of years to get there is the big, actually sending people to other solar systems. And that's a multi-thousand year scale for human civilization, and it's hard to predict what we're going to want to do thousands of years from now. But
quick question. Quick question. Logistic, I guess. Who decides what are the detectors will be going on which telescope? I mean, I assume that the space is limited, and so where's the decisions and who is the decision maker?
That's a good question. And the decision to build something like the Gemini Planet Imager, Gemini, I should have credited, is an international observatory. The US is the largest partner, but also Canada, Chile, Australia, the UK was for a little while, but isn't anymore. And so the committee running that observatory studied possible instruments they could build, ranging from ways to study dark energy to ways to study extrasolar planets. They made, in my opinion, the sensible decision to let other people do the dark energy, because it's silly to everybody to study the same thing and to specialize. Then the next question that's hard for astronomers is who gets to use them. So there's lots of astronomers, not that many telescopes, and so there's a peer review process where you propose a project, and a project could range from I'd like 4 hours on the telescope to study Jupiter, to I would like 900 hours on the telescope to discover a whole bunch of new planets with GPI. And so you have to team up with other astronomers, collaborate, make these proposals to get selected.
So if I understood you correctly, the current models of planetary physics don't explain these massive planets in close orbit around star systems. At the same time, you said that it's possible for very small Earth-sized planets to also be gaseous. Is there models that, it would seem to me that, a close orbit, small mass would almost certainly be solid.
Very close to the star, you'd expect the gaseous envelope to get blown off. And so a planet close to the star probably is made of solid materials, which is not to say it's like Earth. Maybe it was a planet like Neptune that got close to its star and got sort of sandblasted away. So a lot of the models, there are speculative models to explain these. One of the most common one involves making planets kind of the old-fashioned way in the outer parts of the solar system and then moving them around, maybe through multi-planet gravitational interactions like I showed in the simulation, maybe through more complicated processes. So you could make a Neptune, and then if it somehow you move Neptune close to the sun inside the orbit of Mercury, its atmosphere would get kind of sandblasted away and you'd be left with a little core of rock, but not an Earth. So there's just a whole range of possibilities for these planets, and we don't really know what sets the lower limit on gaseous planets or what sets the upper limit. Certainly close in, I agree, they'd get sandblasted. But out at 1 astronomical unit where the Earth is, something half the size of Neptune but made like Neptune could survive perfectly well, and we really don't know whether we make things like that or not.
Is it the pixelization density of your CCDs that's your biggest contributing, limiting factor, or what is your biggest limiting factor in resolution?
In terms of the resolution is set really more by the size of the telescope. So the fundamental diffraction of light sets the smallest size of a feature you can see that's proportional to the one over the size of the telescope. So hence the desire to move to bigger and bigger telescopes to kind of do this. Yeah. Both more light and sharper images you get out of bigger telescopes. But bigger telescopes help you win twice.
Hi. You talked about the use of spectroscopy to determine the composition of distant light objects. I was just wondering, when the light goes through the Earth's atmosphere, is it band filtered by the composition of the Earth's gases, or phase shifted in some way that you have to compensate for that when it's a ground-based telescope?
We do. That's an excellent question. So the Earth's atmosphere is full of, and water would be one example. The Earth's atmosphere's got lots of water vapor in it, not so much in Mauna Kea, but more in Chile. And so we do have to compensate for that. We actually are very lucky compared to other astronomers in compensating for that because in spite of our best efforts, there's always some light from the star left. And we know what the spectrum of the star was before it passed through the Earth's atmosphere. So it's like a beautiful reference source we can use to remove the absorption due to the Earth's atmosphere for both the star and the planet itself.
Do most astrobiologists believe in the possibility of life on rogue planets that are no longer orbiting stars?
I actually probably say most wouldn't. So you saw in my simulation, you can imagine a system in which some planets get flung out by the gravity of other planets. You saw that in the HRD 799 simulation. The same thing could happen to a planet like Earth. The problem is it would cool off very rapidly, so you'd need a source of heat. A planet bigger than Earth would stay warm for a while, heated from the interior. You could imagine life would occur on it, but I would tend to be pessimistic about getting exactly the right combination of circumstances for that to happen. But who knows out there? So there are missions that could potentially see some of these free-floating planets. That's actually another thing WFIRST could do, is have the ability to detect free-floating Earth-like planets through some tricks involving gravitation and answer the question at least of whether they exist or not, but not whether they have life on them.
Is there any thought to advertising that we are here in the universe? Turning it around?
Is there any
thoughts
to advertising? People are discussing this in the sort of SETI, the Radio Search for Extraterrestrial Intelligence community. There have been a couple of signals, but they were sent to completely random stars, so it's not very relevant. There's kind of a debate going on about whether we should do that or not in the universe. My personal opinion is that's a silly debate, because they know we're here if they're out there. They will have their equivalent of the telescopes I just described. They will have been watching this solar system. They will have noticed, gosh, the amount of carbon dioxide in the atmosphere going way up, amount of methane going way down. So, hypothetical civilizations, if you assume their technology is more advanced than ours, which you have to assume, already know whether we're present or not. So maybe we should send an apology, but not a message.
I had a follow-up question on spectroscopy. So you said that the Earth's atmosphere absorbs some of and manipulates the signal that we're getting. So have there been experiments where we try to do this from space, and did that get better results? And in terms of the instruments that are in space and doing spectroscopy, is there a way to figure out that some gas in the interstellar space has manipulated the signal, and is there a way to correct for it?
So this actually right now is an area where the ground-based telescopes do better than space. The Hubble Space Telescope wasn't really designed for this, so it doesn't have the ability to block the starlight. There's no atmospheric turbulence in the way, but there's imperfections in its mirror from the polishing process that scatter light. And so even on Keck, the HRD 799 images, the Hubble Space Telescope can kind of see 2 out of 4 planets on a good day. And GPI is substantially more powerful than Hubble. and the spectrographs on Hubble aren't really designed for planetness. The James Webb Space Telescope will be pretty good at this. There's a whole sub-story involving transiting spectroscopy in the Spitzer Space Telescope that I didn't tell, but I'd be happy to talk about later. But the James Webb Space Telescope will be better at this, and so it will, especially for the water thing, where it's really hard on the Earth because of all the water in the way, it'll be able to get good measurements of water abundances around a large, large number of planets. The interstellar stuff, the good thing about gas in the interstellar medium between us and the stars is it's so cold, it absorbs and emits at very different wavelengths and very narrow ranges of wavelengths, so it's fairly easy to distinguish it from the kind of signal we'll get from a planet, fortunately. So I'm happy to... it's up to you.
Yeah. With your success, are you seeing the future funding improving?
That's a complicated question. It's not obvious, and I don't really have a good answer. So we were funded by this international collaboration to build the Gemini Planet Imager. It's not obvious how we would build one for the 30-meter telescope. I think there's not enough federal funding to identify a path to successfully build the GPI equivalent of TMT that could get to these super Earths right now. Now, there isn't even a telescope to put them on. We've got sort of 10 years to answer that question, because the first thing you do with a 30-meter telescope is not go and look for planets. You want to get the telescope working, do some galaxies, do some easy stuff like that. But I don't actually know the answer to it. These are becoming large-scale projects in a way that especially the US ground-based community, the National Science Foundation, doesn't have the scale of resources to support. So I don't actually have a good answer to what we're going to do for building the next piece of hardware. It's better in space. NASA is good at doing large projects, and potentially there's enough funding to do W first. But especially for TMT and especially for a planet imager, I don't know whether that's going to happen or not, at least before I retire. Okay.
Well, on that uncertain note, let's conclude. Bruce will be around for a little while if you want to come down and ask him questions. Also, the ladies who are running the microphones are astronomers.
And
so
the man,
can,
too.
Please.
Actually, he's an engineer, so your statement is technically true.
Oh,
so.
I'm sorry.
But he's an excellent engineer who works in my lab. So.
Please excuse me.